In the same manner, we want to graph the function y is x squared plus x minus 6 and its derivative function. So let's change this first function to x squared plus x minus 6, and in here we'll do d dx of the same thing. Let's just cut that or copy it, and we'll paste it in here. So we want to plot both of them, and here we are. So we can see that this one is quadratic, and I'm going to do them both in black, and we'll see why shortly. So it's a quadratic which comes down like so. So this one is x squared plus x minus 6, and then this one here is a straight line like so. So this one here is going to be y is d dx of x squared plus x minus 6. Now we want to differentiate y is x squared plus x minus 6, so we know how to do that. dy dx is just 2x plus 1. Comment on any connections you observe between the functions. Well, I'm going to come back to that a bit further on. What is the difference in degree between the function and the gradient derivative function? So the original function has degree 2 because it's a quadratic, so that's just the power on the highest powered term, and the gradient function has degree 1. It's linear, so the power on the highest term is 1. How can we tell before we start that the derivative will have a positive gradient? Well, to start with, the original function is a quadratic, and that means when we differentiate we'll end up with a linear. So it's either going to have a positive or a negative gradient. Then if we consider the x squared plus x minus 6, the highest order term has a positive coefficient. So that would tell us. At what point does the derivative function cut the x-axis? What is the turning point of the original function? So we go for analysis and gsolve and root, and it's the red one we want, so we use the arrow to change to that one, and then execute, and we can see that the root of that is negative 0.50, so that's where it crosses the x-axis. Now if we do a gsolve for the turning point, which in the case of this blue one is a minimum turning point, then we can see that that's at negative 0.5, negative 6.25, and the point we're supposed to notice here is that the x-coordinate of the 0 on the gradient function is the same as the x-coordinate of a turning point on the original function. Now we've arrived at the point here that explains why I drew these in black. So using a red pen, draw on the function where it is positive and increasing. Now that's anywhere from the turning point upwards. We can see that the gradient is positive here and the function is increasing. With a blue pen, where it's negative and decreasing, so the gradient is negative along this section here down to the turning point, and of course at the turning point itself we know the gradient is 0. What happens to the derivative function for these sections? Well, we found just now that the x-coordinates of the turning point and the 0 on this actually line up. They don't quite on my little sketch here, but they're both exactly at negative 0.5 on the x-axis. We know that. So to the left of that, we can see the original function is decreasing, and note how the gradient function is negative. It's below the x-axis. As soon as the function becomes positive, the gradient function is above the x-axis, which is telling us that the gradient is positive. And where the gradient of the original function is 0 at the turning point, this crosses the x-axis, telling us that the gradient is 0.